All right, chapter 5 is one of my favorite chapters, so get ready. It's super fun. So today is just day 1 of notes. Not the most exciting day of notes, but this is a really good chapter, so bear with me. All right, everyone have the new notes packet? It is blue?
Yes.
All right, first day of notes. Here we go. Start with some vocab. So when I say to factor, it means to write as a product of numbers. Product means multiply. So if the directions say to factor, it basically means rewrite using multiplication. All right, first example of the day says give all the positive factors of 42. So we want to list all the numbers that multiply into 42. There they are. When I do this, I usually try to go in pairs, starting with 1. So 1 times what, 2 times what, 3 times what, 4 times what, and you'll end up kind of meeting in the middle. And then when we write them as a list, you just go from smallest to biggest. So you might make a little list off to the side. That's kind of what I do. This is the answer for example 1. So the work on the side might look like 1, 42, 2, 21, 3, 14, 6, 7, and then you kind of run into yourself and you know you already have those. But when we list them as just a list in order from smallest to biggest. But in my head I'd be like 1 times what, 2 times what, 3 times what, 4 doesn't go into it, 5 doesn't go into it, 6 goes into it 7 times. Make sense? Okay. All right. This is the definition for a prime number. A prime number is a whole number greater than 1 whose only factors are 1 in itself. So basically there are no other factors of that number besides 1 times that number. All right, so examples of prime numbers would be like 2, 3, 5, 7, and so on. Any questions? All right. The opposite of that is a composite number. It's a whole number greater than 1 that has more than 2 factors. So other numbers besides 1 in itself could multiply into that number. All even numbers are composite numbers because 2 goes into it, besides 2. 2 is prime. But 4, 6, 8, 10, because they all have 2 as a factor. But there are odd numbers too, like 9 we could get by doing 3 times 3, so it's a composite number. 21 is an odd composite number. 3 and 7 make 21. So as long as there's a number that multiplies into that number besides 1 in itself, it's a composite number. Any questions? So the prime factorization is a way to express the number as a product of only prime numbers. Okay, so you keep breaking the numbers down, breaking the numbers down, breaking the numbers down until you have only prime numbers. The way we do this is through a factor tree. Are you guys familiar with factor trees?
No, my factor is Monday.
Oh, I'm sorry. Whoops. All right, so the cool thing about a factor tree is that it doesn't really matter where you start. Just think of a number that goes into that number. Does anyone know a number that goes into 84?
37.
So 2 and
13. Oh, I said 37.
I think it would be 42, right?
Yeah. I'm sorry.
Now, 2 is prime, right? When we get to a prime, I underline it. Done. That branch is done. Okay? What about 42?
2 and 26.
2 and 21. 2 is done. 21 is 3 and 7. Good. 3 is prime. 7 is prime.
Well, hold on.
Now, when we were at 32, I heard someone say 6 and 7. Is that wrong? No, that's fine. You would have stopped at the 7 and the 6 would have broken to 2 and 3. So you would have still got a 2, a 3, and a 7. We just did it a little differently. Okay? Now, we take all these numbers and we write them out. So 2 times 2 is 2 squared times 3 times 7. This is called the prime factorization. You're writing it as the product of prime numbers.
Wait, do you go off each individual number?
Each branch, each prime number that you underlined needs to be in the insert. Now, the way you check to see if this is right is you multiply it back out. What is 2 squared?
4.
Times 3 is,
12.
and 12 times 7 is?
84.
84, I sure hope. It is. Any questions? Moving on. B. I believe that number is 100.
Yeah.
Okay, 2 and 100.
Yeah.
2's prime. 10 and 10.
5 and 2.
5 and 2. 5 and 2. Prime, 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 prime.
Wait, this Monday.
If you did it a different way, that's fine. But you need to have 3 2's and 2 5's, or you've made a mistake.
But how do you know that the 5 is prime?
Because try to break 5 down further. You can't, so it's prime.
Except for
What about 2?
Ah!
You can break 2 down.
You cannot break 2 down.
2 and 1.
Well, you don't want ones. Ones are meaningless.
But you can break it.
5 down.
You can't.
4 is a prime.
4 you could break down to 2 and 2.
No, 2 and 2. Whole numbers.
You only use whole numbers, and we don't want a bunch of ones. That would not be productive. Okay, this isn't the answer though. What's my answer?
2
times 5.
Very good.
Wait, can you do times 25?
Hey, question. Someone said, could we write that as 8 times 25? No, because neither of those are prime numbers. We want the prime factorization. You should only have prime numbers in your answer. Now, when you're writing this out, go from smallest to largest with the numbers so that we all have them in the same order. Okay? I don't want to have to stop and think like, is 5 squared times 3 to the third the same thing as, just write it from smallest to biggest. Questions? And use exponents. Don't write 2 times 2 times 2. All right.
Wait, what?
Yes.
Can you have
Yes.
as
Yes. All right, I am only going to do a tree for the 180. We'll do the variables at the end. 18 and 10. 5 and 2. 5's prime, 2's prime. 9, 2.
Yeah.
2's prime.
3.
3 and 3. Prime, prime. So I am going to do 2 squared times 3 squared times 5. Now, since these were already written with exponents, now I'm going to write them without exponents. So I'm going to write it as x and y. Just so it's kind of like doing a tree for the variables. We're getting them down to their simplest form as well.
You're doing the opposite.
Kind of.
So,
We're just breaking down the x squared into x and x. You're breaking down the y into just y.
But why would you do that?
It seems counterintuitive, but that's the way we do it. It's just expanding the variables. I know.
I don't like that.
I know. Yes?
So you always put the variables on the last.
Mm-hmm. Yep. Other questions? All right, next we will do GCF. GCF is the greatest integer. That is a factor of all the given integers.
What was the greatest common
GCF stands for greatest common factor. Yep. So greatest means biggest. Common, they both have it. Factor means it multiplies into. So the biggest number that goes into all the numbers that I give you. Sometimes you're finding the GCF of only 2 numbers. Sometimes it's 3 numbers. Sometimes it's 4 numbers. All right, here are the steps. And this is on the back of your blue sheet. So the first thing you want to do is you want to find the prime factorization. So we're going to do a factor tree for all the numbers. Then you want to find the prime numbers that they have in common. We take the lowest exponent of each and you multiply them out. It sounds kind of tricky, but it's not too bad.
Bless you.
So let's say you had like 2 squared times 3 to the 4th and 2 to the 4th times 3 to the 1st, okay? You find the bases that they have in common. So see how they both have a 2?
Yes.
You go with the smallest exponent of the 2. So you'd have 2 squared. See how they both have a 3? You use the smallest exponent with the 3, so 3 to the 1st, and then you multiply those numbers out.
Like all the way.
So like 2 squared times 3. So that's what it means. You find the bases they have in common, and you take the smallest exponent. Sometimes it's actually easier to look back at the tree and see what they have in common. But it's just kind of a personal preference on that one. I think it'll make more sense when we get
Would
into
it get to
examples.
12, or would you keep it like that?
So the GCF, you'd multiply it out and you'd say 12, yes.
Okay. You don't know what to talk about today.
Hey, shh. All right, anyone still writing? Okay, so we want to find the GCF of these two numbers, 40 and 60. The first thing we want to do is find the prime factorization of each.
2 and 20.
2 and 20 will work. Good. Prime. 2 and 10. Prime. 2 and 5. Prime, prime. So I have 2 to the third times 5 is the prime factorization of 40. Now I'm going to do a tree for 60. 2 and 30. Prime. 6 and 5. Prime. 2 and 3. Prime, prime. So this one would be 2 squared times 3 times 5. I'm going to pause there. All right, do you see how they both have a base of 2?
Yep.
What's the smallest exponent?
2 squared.
2. So I have 2 squared times. What else do they have in common?
5.
They both have a 5. 5 to the first. Multiply that out. What is 2 squared? 4 times 5 is
20.
20. So the GCF is 20.
So you wouldn't do anything with the 3.
Nope, they didn't have the 3 in common, so you don't do anything with it. This is where I said it might actually be the most helpful to go back to the original trees and see what they have in common. Like they each have a 2. They each have a 2. They each have a 5. And then do 2 times 2 times 5. Some people are more visual, but. Any questions? The 3 was not a number that they had in common.
No, I'm talking about the exponent.
You go with the smallest exponent. So this was 2 to the third, this was 2 squared. So we go with the 2 squared. Because this one has, they both have 2 2s. This one has an extra 2 that's not in common. All right. Here is B.
So can we break down the
That's a lot.
numbers, like, do 3 break that down, the 7 break that down,
No, don't break down the
the
digits.
whole number.
That's 378. Yep. All right. 179 and 2. Yeah, I was like, I don't think that's gonna work. That.
You want 89?
Because that'd be 8 and then carry the 1. Yeah, that works. All right, 189. How? Yes. 9 times 21. Tim, can you be quiet, please?
Yeah, my fault.
Okay, how do I break the 9 down? How do I break the 21 down?
7 and 3.
Very good. So right now I have 2 times 3 to the third times 7. All right, in the back.
319.
3 times 2.
It would be 313.
Would it be 318?
19 would be 38. It's 3.
Who has a calculator? Just do, yeah, just divide it. What is, yes?
Just use
Divide by 2 and it's 189. Well,
Hold on. Oh, back here. What's this one divided by 2?
that one is 318.
318. Yep. Okay.
It's 3.
318. Yep. Keep going. It's even. Do it again. Hit divide by 2.
159.
Okay. 2's not gonna work, but 3 might.
53.
3 and 53. Okay.
hold up.
It's
So it's 53 prime.
6 and 9.
6 and 9 is 54. Whoop. Hold on.
Whoa.
Wrong button.
Is it working?
What do you think?
It's prime.
It's prime.
Yeah. All right. So prime, prime, prime. Surprisingly prime. So 2 squared times 3 times 53.
Times 3.
All right. So they both have a 2. They both have a 3. What is 2 times 3? 6. Questions? Yes, ma'am.
Just do like GCF equals 3.
Yep. All right. Here's C. So 64 is 8 and 8. And then
40 and 2.
4. Just 4 and 2.
Oh my god.
So we have 1, 2, 3, 4, 5, 6 2s. Now I'm actually going to backtrack from what I said earlier. I'm just going to keep those with exponents. Since now we talked about how you just pick the smallest exponent. For GCF, you can just leave them like that. All right, let's do for 80.
8 and 10.
You can do 40 and 2. I already did 8 and 10. So I'm going to stick with what I got. You should get the same answer.
Is it 5?
5 is prime. All right, so this is 2 to the 4th times 5, a to the 4th, b to the 2nd. So the GCF, they both have a 2, right? 2 to the what? I'm going to write it up here. 2 to the 4th, right? 6 and 4 are the exponents. You go with the smallest one. They both have an a. What's the smallest exponent? A to the 3rd. And then they both have a b to the 2nd. Good.
Now would you have to?
Now multiply the 2 out. 2 times 2 is 4 times another 2 is 8 times another 2, 16.
So be 16 and
Yep. All right, here's D. All right, and in the back.
24 and 2. 12 and 2.
No, 12 and 4.
You could do 12 and 4 at the beginning. That would be fine.
3,
3 and 4,
2.
and then 2 and 2. So we have 2 to the 4th times 3, A, B to the 4th. All right, they both have 2's, right? 2 to the what? 2 to the 3rd. One has a 5, one has a 3, so neither of those are going to work. What about the A's?
A.
Just A to the 1st, good. What about the B's?
B.
Just B, good. What's 2 times 2 times 2?
8.
So 8AB.
You did it.
All right, the last one of the day, and it actually has 3 numbers. But you do it the same way. How do I break up a 12? 6 and 2.
3 and 2.
So that's going to be 2 squared times 3x to the 3rd y. Next, we have 30.
2 and 15. 3 and 5.
So 2 times 3 times 5 x squared y to the 3rd.
2 and 57.
Is it 3 and 19?
Mm-hmm. Good. So 2 times 3 times 19 y. Then what?
2. 2 times
which is 6y.
We did it. What's that thing?
The summary. Don't forget at the end of it. Oh,
There's another one?
there's another one?
No,
No,
we
this is the
already
same
did that.
That's the
Oh, let me. Huh.
Oh, dang, you didn't have it right.
I
on there.
know. Yes, so we learned the definition of two-factor, and we learned mostly about GCF. You could put and prime factorization. So if you are new to this class, we end every class period like this. So you could just put summary and then 3 bullet points. You don't really have to write out the questions. They're the same every day. But the first bullet point is, what did we learn today? So go back, look through your notes. We usually do that one together. The second bullet point, if you're still confused about something, write it here. And then tomorrow when we start class, we'll go over your notes and you'll have time to ask any questions that are still lingering from the day before. So this one's kind of for you to write any thoughts that you might want to revisit tomorrow. And then the third one, I want you to write a sample test question. This has been proven to be one of the best note-taking skills possible, is to write yourself questions. And then the night before a quiz or test, you go back and look through all these. And that's been proven to be one of the best study tools / note-taking skills that you could possibly do. So even if you're not, really wanting to do these are super beneficial. There is research supporting these 3 ideas. So there is a method to why we spend time on this every day. Okay? And we'll start class tomorrow by reviewing the notes and going through and highlighting some things. And then we'll go over homework, and then we'll get rolling on the new material. Any questions?